Hello, Christopher Ray Pre-Calculus students. This is Mr. Lovelace. This is your class lesson video for the week of Monday, March 23rd. This is one video that is for all my pre-calculus classes. At the end of the video, I will have some specific information for both the junior class and the senior classes. So stay tuned through the whole video for the lesson, and then at the very end, a discussion of what's going to be coming up this week in terms of assignment dates, due dates, and so forth. It's important that you watch and all the way to the end and have your calendars ready so you can make a few changes on those. But we're going to start with the book and the packet, which is called Rational Functions Packet. So if your book, you're going to want to open to page 347 and have that available, and then also have your Rational Functions Packet available so we can go over the assignment that I've asked you to do on your calendar regarding that packet. Okay, so first thing, go ahead and grab your book, turn to page 347, and then have your Rational Functions Packet available. I'm going to switch over to the Elmo camera, and the first thing will be page 347 of the textbook. Okay, so on page 347, the topic of graphing rational functions in the middle of page 347. So last week, the focus was on taking rational expressions, rational functions, and factoring them completely. And that was your task on the first 20 problems of this packet, was to just practice factoring, starting with the greatest common factor, and then usually you had either a special form like a difference of squares or a quadratic function that you had to factor into two binomials. Then I asked you, as we were working through some of those problems, to just notice that there might be factors in common that we could cancel out of the numerator and denominator of the function. And then I mentioned there would be, consequences for that in terms of the graphing part. So we'll get into that a bit today in this video. Okay, so just some generic information about rational functions and graphing them. You're going to find on page 347 a pretty good list, overall list of the things or strategy steps that you would use to graph a given rational function. And so first thing to notice is here we're talking about our basic rational function where we have two polynomials indicated as the numerator and denominator. Okay, one thing we haven't done a lot with this year, but it'll be good for us to think about in this context is the graph symmetric either with respect to the y-axis, meaning that if I take a negative value of x, is the function value the same as the opposite value of that value of x, which of course, if you think back to first semester, this relates to even and odd functions. So y-axis symmetry really means it's an even function. And then origin symmetry, this is an odd function, so is the function even or odd? And that tells us something about what the graph looks like. Okay, then the rest of these steps are really kind of what we're going to focus on today is how to take a given rational function and then evaluate the y-intercept by replacing x with 0. This is the way we always find the y-intercept of any function, is to let x equal 0. Find the x-intercepts, which we also call the roots, or the zeros, by solving the equation p of x equals 0. Notice the only part of the rational function we need to focus on when we're looking for x-intercepts is just the numerator. And why is that? Well, we know that the x-intercepts are the values of x that make the function value equal 0. But if we look at the form of this function, this is a fraction. And the only way a fraction is going to equal 0 is if the numerator equals 0. So that's all we have to focus on when we're finding the x-intercepts, is just take the numerator, set it equal 0, solve for x. Those will be the x-intercepts of the function f. Vertical asymptotes, okay? We haven't really talked about asymptote lines. What are they? Well, they are boundaries, right? And they can be vertical or horizontal. Vertical asymptotes are going to be the values of x that make the denominator of our rational function equal 0. In other words, these are places where the function is not defined. Okay, values of x for which the denominator equals 0. In this step, here, we find the x-intercepts by finding the values of x that make the numerator equal 0. Well, in a fraction, the numerator can equal 0. That's no problem. It just makes the whole thing equal 0. But the denominator can never equal 0. So in this situation, this application, those values of x are going to be the ones where the denominator equals 0 makes the whole graph undefined, or the function undefined, which means on the graph we actually have something happens at that point where there can be no part of the graph actually existing. Okay, so the horizontal, vertical asymptotes, you're going to have those at the values of x that make the denominator equal 0. Horizontal asymptotes, so these would be the ones that go that are horizontal lines. That are also boundaries. Okay, it's a little more complicated to find where those are. We'll look at some examples today. And then how do we actually do the graph? Well, once we plot the x-intercepts, the vertical asymptotes, we know kind of where the key points are for the function in terms of the x values. And then we choose some points, right? We make ourselves a little t-chart, find points between and beyond the x-intercepts and the vertical asymptotes. Okay, and then we just try to pull all of this together to help us make a picture. And if you've read through the book, you already have some idea of how these functions tend to look, right? If you don't just look up above, right, here's an example where you have a horizontal asymptote, which is just the x-axis. We also have a vertical asymptote, right? And so rational functions tend to be graphs that have different sections to them, and they always have boundary lines and these unusual sorts of behaviors. And so we're going to see different types of them as we go through these problems. Okay, so I'm going to refer back to this page often, page 347, just so we can go through different types of information as to how to actually do the graphs. Okay, so we're just going to do a couple. So I want you to take out your packet. And we're going to start with number 21. And I do want to pay attention to what they're actually asking us to look at in this problem. So it says for each function, identify points of discontinuity, vertical asymptotes, holes, which we haven't talked about yet, x and y intercepts, and horizontal asymptote, then sketch the graph. Okay. So the very first thing to do is what I've asked you to do actually for all of these problems 21 through 30 is to do what we did last week, which is factor everything. Okay. So you're going to hear me say this often with rational functions. The very first thing you should do is factor everything. Okay, before you do anything, factor everything. Okay, so in this numerator, our greatest common factor is negative x squared. Okay, in general, if you have a negative sign in the front, you want to factor it out. Okay, so we divide out the negative x squared, we're going to get x. And then we're going to get minus 3. Okay, and then you just verify that by multiplying out to get the original back. Okay, then in the denominator, the greatest common factor is x. And then we have x squared minus x minus 6. Okay, one more step is to check that denominator for factors that we can multiply together to get x squared minus x minus 6. And so after a little bit of investigation, we get this. Okay, so that's step 1, is factor everything. Okay, darken this a little bit. Okay, step 2 is now to try to identify these things, okay? Points of discontinuity are first. What's discontinuity? Okay, discontinuity is the idea that if I draw a graph, it's continuous if I can draw the graph by just tracing it with my pencil or without picking it up ever, okay? So lots of things are continuous, straight lines, parabolas, cubic functions, different kinds of graphs, absolute values, square roots. These are all continuous functions, okay? Discontinuity means in order to graph it, I have to pick up my pencil, okay? So we looked at piecewise functions last semester where there's like one section here, then I have to pick up my pencil and go over here and draw another section, then I have to pick up my pencil again and draw another. That's discontinuity. Okay, does this function have any discontinuities? Well, anywhere the denominator equals 0, that's a discontinuity because it creates either a vertical asymptote or a hole, which we'll look at here in 1 second. But at first pass, what I want to notice is in the denominator of this function, I have a factor of x, I have a factor of x minus 3, and I have a factor of x plus 2. So there are 3 numbers that x cannot equal. And x cannot equal 0, x cannot equal 3, and x cannot equal -2. Okay, so there are the discontinuities. These are the places where the function is not going to exist. So when I draw the graph, I'm not going to be able to draw the graph for those 3 values of x. So something's going to happen there. Okay, how do I know what kinds of discontinuity there are? Well, there are 2 kinds for rational functions. There are vertical asymptotes and there are holes. All right, this is where the fun is. Okay, remember how I said that sometimes when these things cancel out, they create a different type of feature. Okay, holes are created in a graph when I identify a common factor in numerator and denominator and I cancel them out. So since the x minus 3 factor cancels out, that's for this value of x, there's a hole at x equals 3, okay? Call this also a removable discontinuity. Why is it removable? Because I can cancel this out. And there's one more in this function, which is the factor of x. I have 1 x here and I have 2 x's here, so one of those will cancel. And since it cancels, that creates a hole. Okay, so once I cancel out everything that's common, what remains is this. Okay, so this function is equivalent to this function because those common factors cancel out. So everywhere where this function has a value, this function has the same value. However, I have to keep these 3 values of x in mind. Even though they cancel out, this function is equivalent to this one, but I still can't use these values of x. Okay, so whatever doesn't cancel out it's still a discontinuity, but it creates a vertical asymptote. Okay, vertical asymptote. That means it has an equation. It's a line, and the equation of the line is just equal to x equals -2. All right, so what we did in that piece was after we factored it, we identified the values of x that make the denominator equal 0. Those are the discontinuities. If they cancel out, like this factor did and one of these x's did, that creates a hole in the graph. And whatever doesn't cancel out, whatever remains as a denominator value of x that makes it undefined, that creates a vertical asymptote. So this graph has 2 holes and 1 vertical asymptote at x equals -2. Okay, once we've done all of that and canceled everything out, now we're going to go ahead and find the x and y intercepts. And the y-intercept is always found by replacing x with 0. So 0 and 0 gives us 0. But notice we have a hole there. All right, so there is no y-intercept because of this. But I'm going to write down 0, 0 because that is the location of the hole in this graph. Okay, so this is a very unusual situation, right? Normally we can put 0 into the function and get the y value where the x value is 0. But in this case, there's a hole there, okay? And that's the location of the hole. It's where it would be, right, if I didn't have this value of x that I had to cancel. Okay, and then the x-intercept, we would set the top equal 0. Well, once again, right, the value of x that would make the numerator equal 0 is the origin, which, as we already know, right, is a hole in the graph. So a very unusual situation. So this graph is not going to cross the y-axis or the x-axis at all. There's going to be a hole right there at the origin. Okay, so that's x and y intercepts. Okay, horizontal asymptote. Okay, in this packet, there's only one thing to remember. And that is if the, and actually in the book, if you want to turn in the book 1 page back to page 345, you're going to see at the bottom of the page, there's a lot of terminology here, but basically what it boils down to is the degree. So if you remember back to algebra, the degree of a function is the highest power of x, okay? And the key thing here in most of these problems is going to be this one. The degree is the same in the top and the bottom. Then if I just look at the leading coefficient, that's the horizontal asymptote. So in this case, the leading coefficients are 1 and 1. There's a negative. So the horizontal asymptote is at y equals -1. Okay, horizontal asymptote, horizontal line has this form. vertical asymptote, vertical line has this form, x equals -2. Okay, so let's draw this thing. Okay, first thing I put in place are the asymptote lines. Okay, so vertical asymptote at x equals -2. So here's -2. Vertical asymptote is just a dashed line through x equals -2, like that. Okay, horizontal asymptote, y equals -1. And again, that came from the ratio of the leading coefficients of our function. So that's -1 over +1. Okay, the degree here, by the way, guys, the degree is 1 on the top and the bottom. Okay, so where is -1? That's right here. Okay, so there's our horizontal asymptote, y equals -1. And here's our vertical asymptote, x equals -2. Okay, we know that there's a hole at 0, 0. So we're just gonna make a hole right there. What that means is the graph is gonna come up on either side of that, but it's not gonna go, there's gonna be a hole right there. And that again goes back to this factor that came out of that picture, out of this part of the function. Okay, so there's gonna be a hole at 0, 0. There's also a hole at 3. How are we gonna find where that hole is? Well, it always comes back to this function after we cancel everything out. We're gonna put that number into that function and find out what it is. So f of 3, right? F of 3 is -3 divided by 3 plus 2. So that's -3 over 5. All right, that's a fraction. It's a little bit less than -1. Yes, a little bit less than -1. So if we go over here to 3, then we also have a hole right there. Okay. And now, how do we know how this graph goes? Well, we're going to choose some test points. Right? This is where you get out your handy dandy t-charts. Okay. And if you look back at the examples in the book, these asymptotes kind of make a little quadrant of itself, right? And this graph is basically going to do this. Okay, it's going to basically make this curve, but we want to make sure we pick a value like an easy one to try, like -1. Okay, we want to see what is this graph doing over here. Chances are it's going up this way. So we put in a -1 here, that makes that positive. And on the bottom we get -1 plus 2, that's positive. So that's 1 over 1, it's 1. Okay, and you can check that. So -1, 1. So that means this graph is going to do like this. And we're just going to draw toward those holes and kind of past them. So it's got this shape like this, but it's got a hole here at the origin and a hole over here at 3. You can put those in here. 3, and we got -3 over 5, but I'm going to write hole. And we got 0, 0, which is also a hole, because those factors factored out. And then last, over here, we know most of the time it goes like this, and then this function over here. We don't have any values over here yet, so we want to actually pick some test values, use this, right, to find the values of the function. Okay, so let's say -3. This would be +3 over -1, that's -3. So -3, -3, there's 1 point on the graph. And if you check a few other ones, right, it's going to go like this. Okay, that is a very detailed description of how to graph these. What I want you to do before our class period, and please send questions to my email so I can get back to you in some office hour time, which I'll announce here in a second, is to go through the rest of these problems. And at a minimum, what I want you to do is factor everything like we did last week, and then identify, right, for each of these, I want you to do this part over here, okay? I want you to find the discontinuities, so that was the first step. I want you to find the vertical asymptotes, that's when the denominator equals 0. The holes happen where the factors cancel out. The x and y intercepts are found in the usual way. We just want to verify they're not holes, for example, like they were in this one. And then lastly, the horizontal asymptotes. So look on those pages in the book that I referenced to help you Okay, so let's start with junior class. Okay, junior class, a couple of changes which I put in the video earlier today that was actually for all the classes, but just so that you guys know what's changed. Okay, basically tomorrow, Tuesday, office hours are still the same. Okay, Wednesday, we're going to change to an independent study day. Your class day will be Friday, and I'll send more information out tomorrow on that, just to remind you. Okay, so class day moves to Friday. Wednesday is independent study, and office hours tomorrow is office hours as usual. Okay, on your lessons, you will see in Google Classroom, there are 4 videos and 1 exercise set under the title of Graphs of Rational Functions. Okay, your Google form assessment, you guys have already done, so this is already done. Okay, in the rational functions packet, as I just mentioned, factor these functions and identify the features. And then on Wednesday, I'll post some more information on video form so that Friday you can have questions for our gathering on Friday. Your lessons will be due Friday at 11:59 p.m. On Khan Academy. There's 1 exercise set. And then I'll also post a Google form assessment, just like I did this past week. Okay, and so that's the overview for the juniors. So if you're a junior, you can stop the video at this point and go back and watch over the example that I did to help you work on the function packet, okay? If you're seniors, continue watching, please, for just a few moments. On your schedule, once again, the beginning is the same. You're going to watch the Khan Academy video. The lessons are in, you're going to watch this video and the one I sent earlier today. Khan Academy lessons are given there. 4 videos and 1 set of exercises. Tomorrow's your work study day, and Friday is also your work study day. Okay, so our office hours will be Wednesday as usual, our Zoom class on Thursday. Your lessons, because of your work study day, are due Sunday. Okay, your Khan Academy and the Google form assessment that I will post. Okay, that was a long video today. Lots going on this week. Please send me questions if you have questions, and I will send follow-up videos as needed to help you with these problems. And have a good week, everyone, and we'll talk to you later.